Hello everyone and welcome to another Würth Elektronik ISOS webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is THR-Soldering Explained: Requirements, Process and Benefits. Our speaker today is Götz Schattmann, who is working as Field Application Engineer at Würth Elektronik ISOS. He will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. Today's webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. And if we are unable to answer all your questions within this time, we will answer them via email after the webinar. And if you still have any other questions left, just email us at isos-webinar@we-online.com. You will also receive the link to the presentation as well as to the recording of today's webinar only in the next few days. But now I want to hand over to our speaker, Götz, and I wish you an exciting webinar.
So, hey, Markus, thank you again for your introduction, and welcome to everyone who joined us today. My name is Götz Schattmann, like Markus mentioned, and I lead you through the seminar topic, which is about THR soldering. Yeah, but first of all, I would like to know a little bit about you. And there's a question, and we are just starting a little survey where you can just answer if you've ever used THR technology. So most of you have chosen their answers. Maybe so that means that about half of you are already in some terms familiar with THR, and 45% said no. Just for your information, so this gives us a rough idea about that. So let's start into the agenda. Give me my pointer. So here's our agenda, what we're going to run through. So at first, how did it come to THR? Then what does that mean to the component in terms of requirements for the basic materials, and how does it look like? So we have some stencil suggestions and what does it mean to your layout. Then we look into the process, also what comes out of the process. So we have to check the quality, and then afterwards, we look on the advantages of THR before we close, and you will have the chance to ask some questions. So how did it come to THR? Yeah, every one of you knows that in the 50s, the THT technology came up, where there's a PCB with a hole inside, and the cable of the component goes through the via and is soldered on the bottom. So it's running over a soldering wave. And yeah, that was the very beginning. Then, of course, the industry raised up, and everyone wanted to have a smoother process and a clear process, and of course, more cost efficient. And therefore, the SMT technology, named for surface mount technology, was invented in the early 80s. Yeah? And what was obvious pretty soon there, if we look here to some kind of connectors, that if you apply force to a connector, it's better if it's a true hole component, so it can absorb much more force. And maybe with the SMT pads, they can be taken off from the PCB. So the solution in many cases could be THR, which combines the advantages of both technologies. But what does that mean to the components, and what has to be changed to make a THT component THR compatible? So, of course, the housing we have to look at, and to the electrical contacts. So if you look at this, very familiar, I think most of you, just the standard pin header. If it has to become THR compatible, it requires some changes, as you can see here. Of course, the plastic is always a point where you have to look at when it's about high temperatures. And you know that for the older THT process, the solder comes from underneath, from the bottom side, and then we have the PCB, and on top there are the components. So the components never gets the same heat like the solder joint. So therefore it's protected in some way. This is not the case, of course, with THR components, because they are soldered in a reflow oven where they get the full heat. And what does it mean to a standard component? Yeah, maybe after soldering it looks like this. So LCP plastic is very usually used now instead of other components materials like PBT, for example, or some polyamides. So LCP has a high temperature, is very high temperature resistant, and is also been used for many SMD components as well. It also has no high expansion rate under high temperatures, or it's about the same like the FR4 material. So that's the material of your PCB. So if they tend to expand, they would do it in the same dimension. So no problem, especially if you have pins that have to go inside the holes and hit the holes. Yeah. And also moisture sensitivity level is named here like MSL level 1. That means LCP plastic does not tend to absorb many humidity out of the air. So you can store it as long as you want, and you don't have to pre-bake or pre-dry it before you use it. So nothing can happen here. What's going to happen for some polymers, like you see the PA9T, which is very common, there is moisture inside, and it tends to absorb also moisture from the environment. And yeah, what happens in the soldering process looks like this. So if the moisture inside expands explosively, then because it's getting hot very quick, then you see the bubbles here, and this one is called the popcorn effect. Maybe you heard about that. So for a component to become THR compatible, it's also necessary that the housing changes. We can't use the same housings, as we know. So we saw this in the intro already. So this is about the same form factor, but it looks different. So what's different? We have some pegs here. These are called the standoffs. Those standoffs, they're building or creating a gap between the PCB and the component itself. So this gap should be at least 0.3 millimeters or better 0.5. So what are they for? Of course, afterwards you can have visual inspection. You can look under it. The AOI, it will be difficult if the camera is on top, but if you look from a side view or from an angle, you can look pretty good under the component to inspect how your solder joint looks like. And yeah, to create a good solder joint, the airflow, and that's the major reason for this standoffs, the airflow has to go under the component to allow a good solder joint here to be created. And also we need some solder paste, which needs to be applied before you set the component, and we need therefore a kind of depot, and the only location we have for that is right under the component, right at the pin. So here you can see get another idea about the airflow. And also metal housings need to be changed, and very often if I explain the standoffs, I show these parts because you can very clearly see those standoffs, that they just guarantee that the component is not sitting directly on the board. So also the pins, of course, need to be customized. And yeah, what can we learn from this example that we show here? We see that the pin is absolutely short. And I think you have the same idea that this solution would not be very stable. The component with a too short pin can tilt or float during the solder process. It is recommended to lead the pins about 0.5 millimeters further so that they come through the PCB. We recommend about 1.5 millimeters for the maximum. If the pin ends inside the via, also the optical inspection must be determined by the manufacturer. So maybe you're not able to reach the standards by the IPC 610, for example. So here's another example. What can we notice here? We see that the pin is very long, maybe like a usual pin that we have for a THT. And in this case, we still recommend that it should come out of the PCB at least 0.5, but to a maximum of 1.5 millimeter. Therefore, we offer our THR components with a pin length of 2.6 millimeters normally to be compatible with PCBs of 1.6 to 2.3 millimeters of thickness. Also for the THR components, a matte tin plating is preferred. This is more suitable to go with the higher temperatures and for a better wetting for the solder that it can expand here. So also what can happen here if the pin is too long? Of course, it's obvious that all the solder is collecting here, and maybe it drops apart, and then you don't have enough solder paste to fill your via. So this is some of the main points that you have to take into account when you look at the components. And one remark from my side, in the very beginning when THR came up, we saw that some manufacturers just changed the plastic materials inside of a component, and then they confirmed it's a THR component, which was not the case because the pins were much too long, and some holding packs, maybe there were like clamps, and you can't force the pick and place machine to push during assembly the component into your PCB, or very limited only, so this would not work. So take care about that. So you also have to take care about some points when it comes to the layout, and of course to the stencil calculation. So let's have a look inside here. Oh goodness, formulas, yeah. But don't worry, we won't go through them all in detail today. But understanding the principle, this is really important. So therefore, on the easily explained, we need sufficient solder paste for an accurate solder joint. And we have to keep in mind that approximately 50% of the volume of the solder paste, of course in unsoldered condition, will be vanished, will be totally gone after the soldering. These are additives and fluxes that evaporate in the process. So the remaining portion of solder paste must, however, still be sufficient for an appropriate connection here. So this amount of solder paste also has to be applied somehow and somewhere on the PCB. And that is why we have, for example, the standoffs that we've just seen. It is therefore important to correctly design the layout for the THR components already in the draft. And if you look to the formula here, you can see T stands for the PCB thickness. Then we have the volume of the via, which is important to know. So we have to calculate that. And inside here, the pin will be inserted. And depending on what kind of shape your pin has, if it's a round pin or a rectangular pin, you have different hole diameters. So for the round pins, plus 0.3 millimeters, and for rectangular ones, plus 0.25. Bigger, so the big hole has to be bigger than the pin, of course, otherwise you couldn't force it in. And if you do it too big, and for THT components, traditionally the holes tended to be bigger than this recommendation. So if you use a bigger hole than that, then there is a rule, not a rule, the risk that you could disturb the capillary effect and the solder paste maybe would not run through all your via. So volume calculation of the pin is something that is important, because we need to know how many solder paste is sufficient. So easy set, the volume of the via, which we saw previously, minus the volume of the pin, which is inserted here. That is the space in between right here and here, and of course it goes all around the pin. And in this calculation, there's no difference if the pin is round or square. You see this A by B, so you calculate it here in the formula. So what we have to add, we already know the volume of solder paste we need inside, and now on top and bottom we need the volume that is there to have the fillets, yeah, which go all around 360-degree on top and on bottom layer. And of course we calculate up to 100% of fill of the via. So I will not run through the whole formula, but yeah, here's an important sentence that you can see marked in red. As mentioned, about 50% of the volume will be gone after soldering. So that means in our calculation, we have to double the amount that we just reached or calculated. So here you can see the PCB, and there's a stencil already on top, and there's the opening of the stencil that needs to be filled. And after stencil is gone, you have your soldering ring and part of the via filled. Best way would be if it's filled up to 80%, and we recommend the stencil height of 150 micrometers. To calculate this, pretty easy, we have created a nice little tool based on an Excel sheet. And also here you see the difference if you want to have a circular pin or if you have a rectangular pin. So you can just fill out the fields here and you get your results here and know what dimension or volume you have to apply for your component, for the pin. So now that we know the amount of the solder paste, how can we get this onto the PCB? Maybe this is more, the volume is higher than we expect, and it's more than we use. Of course, for the THT, we don't need this calculation, because on THT, the solder comes from underneath, from the wave. So now we have to apply it up front here, like for SMD components. And this can also be achieved by overprinting the solder paste on the PCB top side. A sufficient filling of the through hole and overfilling of about 1 millimeter inside the hole is very common. Yeah? And up to 30% of the paste volume can be overprinted. Here, right directly, we print on the solder resist. So here in this picture, the stencil is the gray, is marked in gray. The PCB underneath is green, and the solder pad, of course, is gray again, and white is the holes inside. So 1 and 2 are typically examples for the THR stencils. And so we have the corners also rounded, that the lift of the stencil will not draw any of the paste with it. Yeah. So number 3 is used when more solder paste is required, like the overprinting I was talking about. And also here the edges are round. And now number 4 and going to number 5, those are the opposite direction if you have to reduce the amount. Yeah? And especially here on the number 5 is mostly used when both sides are printed with solder paste to achieve a desired soldering result. That means at first you paste it from the bottom side and you run it once through the reflow as it's melting on the PCB, and then you turn the PCB, you apply the solder paste on the top, like with this mask, and then you set your components, and then you should have enough solder paste depot. So what does it look like? Here you can see an image of a traditional stencil with a squeegee, and so let's look inside here to the process. We saw that before. Here's everything's open, that's the PCB, and here's the stencil on top. Then your squeegee comes running a kind of wave of the solder. So it's rolling the solder over here, and with this rolling effect, you push some of the solder inside the hole as well. And afterwards, you can run this also in 2 directions, yeah, back and forth. On the second way, you can also add more to get more solder paste inside the via, yeah, to have the right fill. Like here, we can see this looks pretty perfect. Then the pin is inserted inside. There's solder paste all around, goes through the oven, and we see a perfect result here. That's how it should be, of course. Yeah. If you notice some problems that maybe not enough solder paste is going to be applied into your into the vias, then you can change some of your settings, like the angle of the squeegee. You have to calculate that it's always, the force is going always in a 90-degree angle. So the force would apply here. If you do it more flat, then the force is going more this way. So maybe this helps a little bit. So if you look to the process stages, we are already here in the paste printing. Afterwards, you will run an inspection if everything's pasted fine. Then you run your pick and place machine where the components are set on the PCB. Many times you have another inspection here. Maybe also manual placement if there are some bigger components like trafo or whatever, which need to be set on top of the PCB, and then it all runs through the reflow oven to the final inspection or the AOI and cleaning. So another stage that we saw here is the pick and place, and you're used to have your components on a reel, so the pick and place machine can just grab it and place it on the right position. So therefore, of course, it's also necessary that your components, the THR components, also come with a cap, or that there is a Kapton foil on top, so the pick and place machine can just pick it and place it. And of course, it needs to come on reels, so you can feed your machine with it. So there's a standard solder profile for the reflow, depending on how much is the volume here of the component itself, how many heat it needs to have, and yeah, I don't want to go into detail. It's more on the production side. But when it comes out of the soldering, yeah, then we have to check and inspect what is the result. And of course, a guideline for that is the IPC A610. So if you look at this, in the IPC, there are different classes depending on what kind of application you have. You have class 1, which is maybe for toys, yeah, up to class 3 here is for most of the industrial appliances that need to be secure in their operation. So they should not fall out during operation. And the important point is the filling level. You need to achieve at least a 75% of filling level inside the via, and also the solder, not the solder source, but the fillet on top should be normally 360, but minimum 330 degrees. And here's the difference, because we're talking about the solder source, and of course with SMD or THR, the solder source is from top, while in the old THT process, the solder source is from underneath, and destination means the direction where the solder has to go. So we see it here. This is what everybody wants to achieve, 100%. If we are lucky if 75% are achieved by the IPC. So let's have a look on some examples here. And my questions to you are the following examples: IPC compliant. So no big guess that this one cannot be compliant, because yeah, there's a lot of solder missing here, and a huge drop is hanging here, so something went wrong and the solder went down here. So the opposite is this one, where there is solder everywhere, even too much of the solder. There's no nice fillet, so this is even not compliant. And what we can see here as well, let me go back. This is something that really needs to be avoided. The solder should never touch the plastic housing. So therefore, this is not compliant as well. So then We often get the question from customers if they can run their THR components even over the soldering wave. And yeah, answer is depends. You expected it, I guess. And here you can see a soldered component, which is a high power terminal. One of our red cubes is fully made of metal, and you can see the solder paste is all filled in here, excepting of some of the gaps here, some lunkers. But yeah, this is working fine now. But imagine this would have been plastic, then this would be absolutely no-go. So here's another picture where you can clearly see the hole was so big that it was just drawn to one side, but this one is still open, so this can never be compliant. This is what it should look like. This is a good cross-section. So what are the real advantages of the THR technology that we just saw? Of course, it offers the mechanical strength that we already know from THT technology. Then the process should be as simple as SMD. And there's only one soldering passage that your board goes through the reflow oven. And we all know that applying high heat to the components always means stress. And therefore, this single passage increases the durability of the components and of the whole board, of course. So then we can make this really process safe, like in SMD. And yeah, it totally save the second production step. So you don't need that anymore. And therefore, it's of course time saving. And you can ship your final product quickly to the customer, which I think he will be lucky about that. So we don't want to hold back that the component price for the THR components is higher. Why is that the case? Of course, the volume of those components is still not that high as for the THT components. And we also saw that we have to use another plastic instead of PBT, polyamide, the LCP plastic is much more expensive. That's not the whole price of the component, but of course it adds up and ends up in a higher price. So then you have to bear in mind that your THR layout is a bit different, even in terms of the stencil, and that you have to apply enough or sufficient paste on your PCB. And of course, if you use the S&D process, you already know your machine, you know which wheel to turn. And this you have to find out for the THR process as well, but then it's absolutely stable. And the master question here is when to achieve the break even, that the higher price is balanced by the savings that you have to save process and to be faster and to have a faster throughput in your production. So at the end, it means a saving in money and a saving in time for you. So a quick summary, you know that I mentioned materials have to be changed for THR components. The pins are shorter, but not only the pins. So we need the standoffs and so on. It combines the advantages of SMT and THT technology. You can achieve a fully automated assembly, and therefore you reduce the risk of failures made by humans. That of course happens. Soldering in a reflow process is a very good and clear and stable process, and can still be optimized. So still it saves time and can save time and money. So I hope within half an hour or 35 minutes, we gave you some ideas. Of course, there are so many questions you might have. We saw them already this morning. Yeah, some of those questions are really particular, but the line is now open and you are free to post your question here. And yeah, with that words, I would like to hand over to Marcus again.
Yeah, so thank you, Götz, for your interesting presentation. Yeah, as you've mentioned, now we would like to turn our attention to your questions. And so we wait a little until some questions come in. Also, in the meantime, just a hint from my side, you will receive the link to the presentation you just saw, as well as to the recording of today's webinar the next few days. So then, let's start with the first question. Götz, would you always apply paste on both sides of the board when you have SMD components on both sides?
General answer, it depends. I think you don't expect this answer, of course, but maybe you know it. Generally spoken, if you have a connector, like for example, a USB-C, where we have had some points to get a stable result, we had the point that we really found out you have to apply solder paste on both sides. And at this very point, I don't see why this should not be possible. So yeah, the components, the SMD components itself, they can run at least 3 or 5 times through the reflow oven if they are standardized like that. So it doesn't look like a problem to me.
Okay, thank you very much, Götz. Then let's go on with the next questions. When it is soldered, must there be a fillet on the bottom side?
If we talk about THR soldering, I mentioned about the IPC, and they were talking about the solder source. And the solder source side is that side where you need to have a fillet. Yeah, and oops, sorry. So it's not absolutely necessary that you have a fillet underneath there on the bottom side. So, but it needs to be under the component, so under this connector that we saw, for example.
Okay, thank you very much, Götz. Then just a hint, another hint as we also wait for some other questions. If you have any questions left after the webinar, just email us at isis-webinar@we-online.com and we will try to answer all your questions promptly. So, but then, Götz, let's go on with the next question. Is it possible to solder a THR part with wave soldering?
Yeah, generally, yeah, I mentioned this also before that generally spoken, it's possible. The also depends on the thickness of your PCB, and the pin should go all through the PCB, at least 0.5 millimeters. If you want to run it over the wave, it should be a little bit longer, so maybe you only do it with 1.6 millimeter PCB thickness. Generally, yes, it works. However, you really need to avoid that the solder paste is rising up or climbing up until it touches the plastics, because this is not allowed by all these standards, not only by the IPC. So if you can make this clear, and once again, you have to check, you have to run trials, and then you find out how it works best.
Okay, thank you very much, Götz, for your explanation. So I think now we are finished with our webinar. if there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you really enjoyed our webinar. Also, big thank you to you, Götz, for your time today and your engagement.
Yeah, also thanks to everyone, and bye-bye.
Also for me, have a good day and goodbye.